Number 14. Number 14 reads, the dome of a Van de Graaff generator receives a charge of 1.9 times 10 to the negative fourth coulombs. The radius of the dome is 1 meter. Hint, consider the properties of conductors in electrostatic equilibrium. Also, because the points on the surface are outside a spherically symmetrical charge distribution, the total charge may be considered as located at the center of the sphere. Part A, find the magnitude of the electric field strength inside the dome. B, find it at the surface of the dome. And then C, find it 4 meters from the center of the dome. Well, the first thing is, before we dive in, let's kind of visualize what's going on here. This is one of the computer simulations that we did, looking at trying to visualize the field around different charges here. This is, in this case, 3D, okay? And we just take a slice here, which is kind of cool. The Van de Graaff was a giant steel dome, if you recall, where we charged it up with a bunch of electrons, and then we had your classmates' hair fly out. We sat people with the Leyden jar. We had the fur flying, all sorts of mayhem, okay? So it's a fun way to visualize the space around a charged object changing, creating a force field. And since it is a negative source, a positive test charge will be pulled inside there, is a way to visualize it, okay? So that's kind of the common sense picture of what's going on here. So anyway, let's go ahead and set up this problem here in number 14. So step one, let's sketch out the situation here. What is a Van de Graaff generator? It's basically a giant steel dome, and on top of that dome, there's a column underneath, rather, with a belt that can strip off a lot of electrons off a felt or wool roller, and then that rubber belt charges up the dome by friction. It piles on a bunch of negative charges there. Think of it that way, as a way to visualize how Van de Graaff works. Okay, and that's pretty much it. Step two, let's go ahead and list all of the information that's given in the problem. So in step two, we were just given the amount of charge put on the dome, 1.9 times 10 to the negative fourth coulombs, and the radius of the dome is 1 meter. That's awesome. That's a huge Van de Graaff. Ours is not that big. And the bigger the dome, the more charge you can pile on. And then we have to answer a couple things. The first thing is, not our toolbox, the strength of the electric field inside the dome. Well, this is not really a math problem, but inside the dome, inside any metal conducting shell, the electric field has to be 0. Okay, so the electric field inside a metal conducting shell is 0. And that's a conceptual question. This is a Faraday cage, and inside the net field will cancel out because the charges distribute to equilibrium. So if you put a positive test charge there, it would just zero out. We're completely shielded. So the whole point is, inside a metal conducting shell, there are no electric fields. The field lines cannot penetrate, and they fly out perpendicular to the dome. That's part A. Next part of the question, find the magnitude of the electric field strength at the surface of the dome. So we're trying to find E at the surface of the dome. And again, since they say that the charges are all distributed evenly, we can treat a little hint as if all the charges were right in the center here, theoretically, okay? So we're going to look in our toolbox, and we can find an electric field, which is a force per unit charge, or we'll have to use the KQ over the R squared form in our toolbox here. So here we go. In step 3, let's go ahead and write out, instead of the E equals F over Q equation, we need the KQ over the distance squared here. So notice this is just a special form of Coulomb's law. But in this case, we're not looking at the electrostatic force, but the electric field force due to a source of charge here. So now it's just simple plug and chug in step 4. We take our information from before and we substitute it in. So the strength of our electric field will be equal to E times K. K is the electric field constant, which is 9 times 10 to the 9th Newton meters squared over Coulomb squared. Straight out of our toolbox right here, 9 times 10 to the 9th Newton meters squared Coulomb squared. Right there. Multiply that by Q, the amount of charge present, 1.9 times 10 to the negative fourth. And then we divide that by the distance squared at the surface. So in this case, it's pretty straight up. Let's get out our calculators and plug in. So if I do 9 times 10 to the 9th, multiply that by 1.9 times 10 to the negative fourth, divide that by 1 squared, don't have to do that. We get a big number. And a little trick is, if you want to put that in scientific notation, just hit mode, select science for scientific notation, quit out of there. And then our previous answer we can express as 1.71 times 10 to the 6 newtons per coulomb. It's a force per charge on our force field. So that was part A. This was part B. Now in part C of the question, it says, find the magnitude of the electric field strength 4 meters from the center of the dome. So now our radius, we're going to set to 4 meters. And we do the exact same thing. And it's kind of common sense where if you are 4 times further away, the field's going to be weaker, but it's going to be not 4 times weaker, but 4 squared, 16 times weaker. Or if you look at our little simulation here, you can see that kind of like a black hole here. Okay, if you're way out here, think of like you're sledding, okay, something like that, into a black hole. As you get further out, the field's a lot weaker versus closer up, right? So practically speaking, when it comes to electrostatic safety, you never want to be the closest thing to a high voltage source, like a thundercloud or a high voltage power line, etc. So anyway, let's just go ahead and do the same thing. The only difference is this time we divide by 4 squared, which is 16. So basically it's just our previous answer, what we just got, and we'll divide that by 16. And we get 1.068, 1.069, good enough, times 10 to the 5th. Newtons per coulomb. So, in a nutshell, that's number 14.